Selection of analyzers. General. Analyzers should be chosen from the list of selected vendors provided by the principal. If a specific analyzer is not on that list, or if the list itself is not available, the contractor should consult the principal for guidance. The principal is responsible for preparing the list of selected vendors, which is based on satisfactory information about the manufacturer, including submission of the company profile, QA/QC procedures and compliance progress with ISO 9001, sales references, required documentation, certification for use in hazardous areas, if applicable, test reports on performance, standard consumables and projected annual costs, spare parts list and costs, information on post-sales technical assistance, manufacturer's documentation. The manufacturer's documentation for the analyzer should include instruction manual with installation practices, operating manual, service manual. The manuals should cover data sheets on the application, startup instructions, troubleshooting instructions, scheduled maintenance instructions, validation calibration instructions, drawings for layout, flow scheme, wiring, circuit diagrams, and termination, parts list, list of consumables, fragile spares, initial spares, and spares for 1 year's operation, electrical safety certificates, and supporting documentation. Construction. The principal specifies whether the enclosure protection should be based on IP codes, IEC 6529 or NEMA 250. The manufacturer must confirm the selected enclosure protection. The enclosure and other components must be protected for the environmental conditions where they will be installed, such as tropical or saliferous conditions. Sample-wetted parts must be suitable for the fluid and conditions, typically made from AISI 316 stainless steel, polyfluorochlorinated plastics, or glass. Instrument components should be accessible for servicing with minimal disturbance to other components. Calibration or validation adjustments should be possible from the front. Hermetically sealed relays, switches, and potentiometers should be used, and other electrical contacts should be gold-plated. The use of asbestos or polychlorobiphenyl, PCB, compounds is not allowed. Electrical terminations must be compatibly labeled at the wire and terminal or at the cable connector and socket. Fittings should be AISI 316 stainless steel with metric or imperial size as specified by the principal. Functional performance. Functional performance must satisfy the principal and may be judged from manufacturer's in-house tests witnessed by the principal, shell group experience, evaluations tests by independent testing authorities, experience reported by third parties, typical characteristics of specified analyzers. Sections provide recommendations for selecting analyzers based on measuring techniques, with priority given to the list of selected vendors. Analyzers should align with the relevant ASTM test method used in the site laboratory. Analyzers for environmental pollution control or continuous emission monitoring system, CEMS, may need approval from local authorities. Key characteristics for various analyzers. Composition. Multiple component analysis typically uses PGC or mass spectrometers. Infrared and ultraviolet spectroscopic techniques are suitable for single component analysis of gases and some liquids. PGCs can calculate derived physical properties. Density, relative density. Density meters should be of the vibrating type, with radioactive types requiring principal approval. Dissolved oxygen, measured with a polarographic cell or metal electrode type meters. Flammable gas detection, refer to specific guidelines for ambient air. Flashpoint analyzers should detect the flash on explosion. HCl measurement, use conductivity-based analyzers or paper tape impregnated with reagent. H2S measurement. Different methods are recommended for low and high concentrations. KVP measurement. RVP analyzers are recommended for correlation. Moisture measurements. Several techniques are recommended, each with specific applications and limitations. Octane analyzer. Near-infrared analyzers are preferred where specifications can be met. Oil in on water. Different methods are recommended based on the type of oil measurement needed. Oxygen. Different types of sensors are recommended based on the application. pH measurements. Electrode-type meters are recommended within certain pH ranges, titrators for extreme pH values. Phenol in water. Colorimetric-type analyzers are recommended. Pour point measurement. Analyzers detecting surface motion are used. RVP, read vapor pressure analyzers are recommended. Salt and crude, a batch-type analysis measuring conductivity of the extract. Stack gas composition analyzers must meet local environmental regulatory authority requirements. Sulfur, different methods for high and low concentrations. TOC in water, UV oxidation technique is preferred for environmental measurements. Viscosity, capillary-type viscometers are recommended for optimum precision. Water analysis, various methods are recommended for chlorine, ammonium ions, alkalinity, and COD. Specification of analyzer. The successful use of an analyzer depends on a good understanding of its need, requirements, and the prevailing process conditions by both the principal and the manufacturer-supplier. Typical analyzer applications for various processes are listed, and an analyzer narrative template should be completed to document the justification for the analyzer. Application details must be thoroughly discussed between the principal and manufacturer-supplier. Before detailed engineering and selection of analyzers, the manufacturer-supplier's analyzer datasheet must be completed and agreed upon by all relevant engineering disciplines. The aspects of sample transport and sample conditioning must be duly covered and agreed upon. Typical requirements. Typical requirements that should form part of a requisition include the type of analyzer, the composition, quality, and/or physical property to be measured, the measuring range, the relevant ASTM or equivalent test method, the required precision and maximum bias, technical data for the analyzer components such as analytical part, control module, power supply, etc. Speed of response, the construction type with respect to electrical certification, enclosure, mounting facilities, and fittings used. The electrical construction must comply with relevant standards. Additional information to be supplied to the manufacturer/supplier. Typical information that must be supplied to the manufacturer-supplier includes area classification suitable for the analyzer, environmental conditions suitable for the analyzer, service, such as top reactor, etc. The product, such as kerosene, distillate fuel oil, residual fuel oil, etc. The composition of the product or the components, physical property, etc. of interest. Normal, minimum, and maximum values must be reported, including trace amounts of possible contaminants. Alarm settings, if any. Output signals format and interface to DCS. Sample properties at sample takeoff and return point, such as pressure, temperature, absolute viscosity, density, molar mass, gas and liquid, liquid and gas, water in sample, solids in sample, solids particle size, cloud point, pour point, dew point of gaseous sample, and bubble point of liquid sample. Normal, minimum, and maximum conditions for sample takeoff. Normal and maximum conditions for sample return. Available utilities such as voltage, frequency, instrument air, tool air, demineralized water, potable water, cooling water supply and return, nitrogen, and available flare header. Typical information to be requested from manufacturer-supplier. The manufacturer-supplier must advise the principal of the following: precision and bias for the typical application, method of calibration, speed of response, nominal, minimum, and maximum inlet and outlet conditions for the analyzer, response cycle time, safety precautions in the event of failure, required ambient conditions, maintenance requirements of the analyzer, deviations, if any, from the requisition, interference effects, interface with DCS signal format such as 4 mA to 20 mA, Modbus serial link interface, etc. Output signal format, bottle gases if required, type and purity, recommended spare parts and costs, auxiliary equipment, chiller, vortex cooler, etc. Documentation. The language used in the documentation must be English, unless otherwise specified by the principal. The documentation is intended for the purchasing department, the startup team, the service team in the field, 1 document per analyzer, and the maintenance workshop library. The type of documentation and numbering must be specified with the order. The documents should be available in hard copies or electronic format. Purchase requirements. Specific details of the required analyzer must be specified in the requisition. Calibration and testing facilities. Where special test equipment is specified to facilitate calibration, testing, and checking of the analyzer, such test equipment must be part of the order. Calibration gas cylinders with the appropriate calibration gases and all necessary equipment, such as pressure regulators, Sensor head connections, fittings, etc. should be part of the main order. Cylinder connections must be compatible with local standards. A certificate must be supplied with every cylinder, stating the composition of the gas contained, the date of filling, and the expiry date. A FAT should be specified and witnessed by the principal or their representative unless waived. Auxiliary equipment. Auxiliary equipment, chiller, vortex cooler, air conditioner, etc., that forms an integral part of the analyzer must be clearly specified. The principal must be advised on the use of standalone auxiliary equipment that may be sourced separately or shared with other analyzers. Design, engineering, and installation of an analyzer. Design study, location of an analyzer. The first objective of the design study should be to install an analyzer in an analyzer house with artificial ventilation. Control units, such as microprocessors for PGCs, may be remotely installed in other suitable premises, such as the auxiliary room of the CCR or FAR nearest the analyzer equipment. Engineering of the analyzer system. General. For instrument installation practices, relevant standards should apply. The standards of protection are not limited to the following options: intrinsically safe, XIA or XIB as appropriate, pressurized, XP with type certification, flame-proof, EXD, pressurized, EXP with item certification, non-incentive, XN. The electrical installation should comply with relevant guidelines. Analyzer location. The analyzer should be located close to the sample takeoff point if this does not adversely affect performance or maintainability. If not, the analyzer should be in a walk-in shelter or an analyzer house. The required environment, such as humidity, temperature, and area classification, may necessitate the use of an analyzer house. The following analyzers are typically suitable for location in a walk-in shelter: oxygen meters on flue gas in stacks or ducts, pH electrode type meters, electrical conductivity meters, dissolved oxygen analyzers, density meters for absolute density measurements, moisture analyzers, H2S SO2 ratio analyzers on sulfur recovery clause units, analyzers handling very viscous products, analyzers monitoring gaseous products, analyzers for monitoring the composition of gaseous products, requiring the best possible precision and bias, should have the outlet of the measuring cell vented to a vent system at constant absolute pressure or electronic compensation for barometric pressure changes. Analyzers with thermostatic baths or chillers. Samples entering thermostatic baths should be within 10 degrees Celsius of the bath oven temperature, or less if specified by the manufacturer. Some analyzers, such as those for freeze point, cloud point, or pour point, require an external chiller unit. Ambient temperature affects the performance of the chiller unit and analyzer Peltier elements. In tropical countries or locations with ambient temperatures above 30 degrees Celsius, the chiller unit should be sized for sufficient cooling of the sample at the highest possible ambient temperature. The chiller unit should preferably be installed inside an air-conditioned environment. Dry air or nitrogen should be used to purge the reservoir space to prevent icing and water condensation. Electrical protection. The inside of an analyzer house with artificial ventilation should be classified as non-hazardous. However, certain recommendations must be followed. All electric and electronic enclosures inside an analyzer house that may not be de-energized upon ventilation failure should be suitable for installation in Zone 1 or DIV. 1. Hazardous areas. All electric and electronic enclosures with an internal flammable source of release should be suitable for installation in Zone 1 or Div 1 hazardous areas, regardless of the area classification. Gas group and temperature class requirements depend on the process area classification and the internal flammable source of release. Power supply. AC-powered apparatus should match the site power supply voltage. Separate step-down transformers should not be used. Output signal. The preferred method of data transfer to a DCS is via a serial link, which should provide single-loop integrity or be redundant. The configuration is subject to the approval of the DCS design engineer. Digital data transfer between equipment of different makes should comply with the Modbus RTU protocol. Measuring range. The measuring range should provide optimum precision and prevent a false sense of accuracy. Guidelines for measuring ranges include electrode type pH meter, typical range is 4 to 10. Electrical conductivity meter, optimum range is 2 decades. Light absorption spectrometers, optimum range is 2 decades. Pump-driven capillary and rotating type viscometers, range should be expressed in absolute viscosity units. Moisture measurements, units depend on the meter type, e.g. mirror type dew point, Carl Fisher, metal oxide, P2O5, absorption type, hygroscopically coated vibrating crystal, silicon sensor, fiber optic. Utilities. All utilities except instrument air should enter the analyzer via the sample conditioning system. Instrument air or nitrogen gas may be brought to the analyzer via the sample conditioning system or directly from the analyzer house header. Vent and drain outlets. Vent and drain outlets should be routed via the sample conditioning system rack. Gases and vapors from products should not be vented to the atmosphere unless approved by the principal. Certain analyzers, such as PGCs and spectrometric types, may require an outlet at near atmospheric pressures and at very constant back pressure. The measuring cell outlets should be vented via a gas recovery system to process or flare. Computer-assisted functions. Analyzer equipment should be microprocessor-based, aiming at a high degree of self-diagnostics and supporting online statistical control of validation and calibration procedures. Such equipment should be compatible with the AMADAS functionality. Inspection and testing. Factory inspection and testing. General. Inspection and testing at the manufacturer-supplier's works should be carried out in accordance with standard procedures. Acceptance test. The analyzer should be tested at the manufacturer-supplier's works to demonstrate proper functioning before shipment to the site. The principal should be invited to witness the FAT. Testing should include a full check of operational requirements and the proper functioning of all hardware and software in the system. This includes a full functional check, fault diagnostics, stability run, and a test run with a sample with properties close to the process sample to prove the analyzer's accuracy and precision. Site inspection and testing. Site inspection and testing should be carried out according to standard procedures. Calibration and testing during startup and commissioning. General. At initial startup, analyzers must be calibrated to match the output signal to the reference value. Calibration and test records. For record purposes, a specific calibration sheet should be completed after each calibration and a test sheet after each test. These sheets should clearly indicate the date, the name of the technician, and the type of calibration or test. The sheet could be in electronic format forming a part of a computerized maintenance management system, such as AMADAS. For PGC, a signature chromatogram should be included. A signature chromatogram is the as-built chromatogram for future reference and troubleshooting. Test mixtures. Gravimetrically prepared standards. Gravimetrically prepared standards are traceable to mass standards and weighing procedures, and to the sources of their constituents. This standard should be used for calibration of analyzers, measuring the composition of a product when maximum accuracy is required. The supplier of the mixture should submit the results of the gravimetric procedures. These results should be referred to as the true value. Traceable standards. Traceable standards are products that, by analysis, have been compared with samples obtained from an official standardization center. The precision cannot be better than the precision of the analytical method. Certain analyzers, such as cloud point analyzers and flashpoint analyzers, can be calibrated against traceable standards obtained from the principal's main laboratory or from a quality surveyor, in which case the certificate of analysis should be used for calibration. Secondary standards. Secondary standards are traceable to either a gravimetrically prepared standard or a traceable standard, and may be used for checking or testing purposes. A secondary standard is typically derived from material collected from a suitable location in the process. Procedures for calibration verification of analyzers. General. The normal method of calibrating and verifying analyzers is to introduce a suitable test sample. When more than one party has an interest in the integrity of the analyzer, such as in cases of custody transfer, the method and procedure should be subject to mutual agreement between the parties. Composition, PGC, Infrared and ultraviolet spectrometers and mass spectrometers should be calibrated with test mixtures. Additionally, mass spectrometers require gravimetrically prepared binary mixtures for each component analyzed and/or interfering components. Conductivity. The electronic part of the analyzer is checked using a decade resistance box for 10%, 50%, and 90% of the span. A portable conductivity meter, calibrated in the laboratory, may be used to verify the analyzer's performance. A grab sample validation check for very low-range samples is not recommended as the reading changes when the sample is exposed to the atmosphere, thus requiring very careful sampling practice. Density, relative density, vibrating type. Absolute density meters should be calibrated according to the manufacturer's instructions and performed under laboratory conditions. Verification may be done by checking the inherent frequency of the vibrating spool of the sensor at near-vacuum conditions. Another method is to inject UHP-grade nitrogen gas at various pressures and compare the output readings with the IUPAC nitrogen density chart at corresponding pressure settings. Grab sampling may be an alternative for gas density analyzers, provided that temperature and pressure during sampling can be measured accurately. Relative density meters should be calibrated with pure gases of different molecular weights. Dissolved oxygen. The normal method of calibrating a dissolved oxygen DO meter is by exposing it to air. The manufacturer's instruction manual should be followed for the detailed procedure. Calibration should not be performed by passing the sample through an oxygen scavenger. One way of checking the zero point of a DO analyzer is to immerse the sensor in a prepared solution of distilled water mixed with a few teaspoons of sodium sulfate. Flammable gas detection. Refer to specific guidelines. Flashpoint analyzers. Flashpoint analyzers should be calibrated with a traceable standard or a secondary standard. The range of calibration should not exceed 20 degrees Celsius. H2S gas detection. For H2S in ambient air, refer to specific guidelines. For H2S in process gas, a grab sample analyzed in the laboratory should be used. Moisture measurements. Refer to the relevant section. Oxygen. Initial calibration of zirconium oxide type meters should be carried out with 3 test gases: low span, mid span, and high span. Subsequent recalibrations may be done with low span and high span test gases only. Paramagnetic type oxygen meters should be calibrated with zero gas and air as span gas. The composition of the zero gas should reflect the background gas at process conditions. Polarographic type oxygen meters should be calibrated with zero gas and span gas. If the measuring span exceeds more than 1 decade, mid-span gas may be required. pH measurements. Calibration of electrode-type pH meters should be carried out with buffer solutions with a wide temperature range. Online pH meters may be verified with a portable pH meter certified by the principal's main laboratory. Comparing pH values from online pH meters with samples analyzed elsewhere is not reliable. Titration-type pH meters should be calibrated by means of gravimetrically prepared samples of known pH. Maintenance, calibration, and testing during normal operation. General maintenance, testing, and calibration of analyzers are usually carried out by the principal's site service organization or by a third party under a service contract. Initial readings, output values versus reference values, and response times should be recorded in the relevant part of the site Instrument Analyzer Maintenance Management System, such as AMDAS. Maintenance. Scheduled maintenance of analyzers includes visual inspection at specified intervals. Any observed deviation from desired conditions, such as flow, pressure, temperature, etc., should be corrected and recorded. Test calibration frequencies. Initial calibration and test frequencies should consider the manufacturer's recommendations. As system performance is recorded over time, test frequencies should be adjusted to ensure optimum performance. When the analyzer is tested for performance, adjustments to match the output signal to the reference value should be carried out only when the difference exceeds the specified tolerance limits. These tolerances should be subject to statistical control and should depend on historical verification data. General purpose of analyzer houses. The main purpose of an analyzer house is to ensure the continuity of operation of analyzer systems at a specified rate of reliability by providing a suitable operating environment for analyzers which cannot otherwise operate properly if exposed to outdoor ambient conditions. The operating environment may be affected by requirements concerning area classification, environmental conditions, mainly temperature and humidity, sample handling and conditioning, effective maintenance. As analyzer houses are complex and expensive in both CapEx and OpEx, they contribute significantly to the total cost of ownership. Therefore, they should only be erected when strictly required, and their size should be optimized in accordance with this DIP. In selecting the measurement methodology, it should be considered whether the required operating environment can only be provided by an analyzer house. The suitability of cheaper alternatives, such as a walk-in shelter, should be checked. The selection of either a walk-in shelter, a site-erected analyzer house, or prefabricated analyzer house, with all analyzer systems installed, should be evaluated in terms of total cost of ownership. Basis of design. This specifies the design and construction of analyzer houses with regard to provisions to maintain a non-hazardous area with regard to flammable gases from possible external flammable gas atmospheres and from internal releases of limited extent. Protective measures in case the above provisions fail. Safe procedures for producing and maintaining the installed electrical protection measures. Maximum and minimum limits for climatic conditioning, if required. Verification and testing of installed instrumented protective systems. Hazardous situations created by external toxic gas atmospheres should be dealt with separately for each individual case. Recommendations are given for the design, construction, and operation of systems for forced ventilation of analyzer houses, for their associated equipment such as air ducts, and for the auxiliary devices necessary for providing and maintaining the required conditions by ventilation and overpressure above ambient. For the purpose of this DEP, analyzer houses are assumed to have forced ventilation systems. Induced ventilation systems should not be used. Hazardous situations arising from the toxicity of gases and vapors which have to be handled should be the subject of a special study, on the basis of which the appropriate measures should be decided on and submitted to the principal for approval. Hazardous situations arising from products in the process environment around the analyzer house should be addressed in the plant hazard study during the preliminary and final design study. Basic design standards. The following standards should apply in conjunction with this DEP. IP15 for ventilation requirements of analyzer houses and adjacent sample conditioning areas. IEC TR 6079-16 for the procedures to achieve a safe area inside the analyzer house that satisfies IP15. IEC 6185 for maintaining the integrity of the analyzer house and its direct vicinity. Health, Safety, and Environmental HSE considerations. The following HSE measures should be taken to ensure that the interior of the analyzer house can be classified as non-hazardous under normal operating conditions. The quantity of flammable materials entering the interior of the analyzer house should be kept to a minimum. This should be achieved by applying relevant DEP guidelines. An efficient air ventilation system should be provided to continuously dilute accidental internal releases of flammable gases or vapors, if any, to below the levels recommended in IEC TR 6079-16. To ensure that electrical equipment does not create a hazardous condition if the ventilation system should fail, additional precautions should be taken. Provision of systems for safe disposal of waste material should be ensured. For example, if the vent gas from analyzer houses is continuously contaminated with hydrocarbons, then an environmentally acceptable and safe means of disposal of this vent gas should be provided. Provision of fire protection features should be as described in relevant DEP guidelines. Location of analyzer houses. Analyzer houses should be located in a non-hazardous area or a Zone 2 area. They should not be located in a Zone 0 area or a Zone 1 area. The location should be at least 15 meters away from furnaces. Ensure that the vibration level does not exceed that specified for the equipment accommodated inside the analyzer house. Be free from spills of water and process liquids. Locations under pipe bridges or other structures should be avoided. Civil engineering aspects of analyzer houses. General, an analyzer house typically comprises the analyzer room, which should have forced ventilation to ensure it is a normally non-hazardous area. Sample handling areas on the outside of the longest walls, back to back with the analyzers inside. These areas should be designed so that the area classification does not become more hazardous than Zone 2. Building standards. The construction of analyzer houses should be in accordance with relevant DP guidelines and one of the following drawings. S17.001, typical analyzer house for tropical areas. S17.02, typical analyzer house for non-tropical areas. In addition to the above, the following aspects should be attended to. Connection of effluents from the vents and drains to a dedicated collection sump or vessel located near the analyzer house. Potable water supply, and the recommendation that its piping and fittings should be designed to prevent back siphonage. Material for the sink. Fire call button outside the main entrance door. Construction and layout requirements. This DEP deviates from IEC 61285 on the following subjects: spare space as per Part 5.3, ventilation requirements as per Part 5.5.6. In addition to IEC 61285 and IEC TR 6007-916, the following aspects should be considered. Openings in the analyzer house should be provided for. Electrical power and instrument signal cables to enter and leave the building. These should be in the corners of walls at floor or ceiling level. Ventilation air inlet ducts. Ventilation air outlet ducts or louvers. Sample and utilities inlet and outlet lines. Any other services deemed necessary by the principal. The minimum walk space between fixed obstacles should be 1,000 millimeters, considering that cabinet doors may be locked in the open position on one side at a time. The internal length should suit the number of analyzers to be installed, plus a further 20% spare. There should be sufficient clearance between cabinets and equipment to allow for maintenance access. Door dimensions should allow free access for analyzers and analyzer racks and should be 0.90 meters wide and 2.10 meter high. Doors should be fitted with door closers. Rooms should have exits at both ends if flammable or toxic materials are stored or handled therein. Space, the sample handling area, should be reserved on the outside walls of the analyzer house for the installation of sample conditioning systems, and should allow the analyzers and sample conditioning systems to be installed back to back. The length and height of this sample handling area should be the same as that of the analyzer house. The unobstructed walk space should be a minimum of 750 millimeters. The degree of weather protection of the sample handling area depends on local conditions and the required condition inside, but should include at least a canopy. Sample handling areas can typically be of fully open construction for use in mild climates, CS701, of partly enclosed construction to provide protection for sample handling components against cold and harsh weather conditions, CS17002, but still with adequate, natural ventilation. The principal should be consulted if a fully enclosed sample handling area is required. Sufficient space should be provided inside the analyzer house for the installation of a sink, workbench, and auxiliary equipment, such as control units and, if required, recorders, signal converters, printers, computer terminals, etc. In view of the possibility of accumulation of hydrocarbon spills, drain pits are not allowed inside the analyzer house, but should be located outdoors instead. Door sills should be flush with the floor to prevent tripping hazards and to allow hydrocarbon spills, if any, to be flushed to the drain pit outside. The roof should be nominally flat, with a slope of at least 1/100. No equipment, e.g. an HVAC unit, should be installed on the roof. Otherwise, the analyzer house should be provided with a permanent ladder on the outside, a galvanized steel catwalk for access to the roof, and a roof railing for personnel safety. For structures on the outside of the analyzer house, fire-retarding materials other than steel should not be used unless approved by the principal. Additional requirements for prefabricated analyzer houses. Concrete should be used as the material for prefabricated analyzer houses. Design and finish should be based on a 20-year lifetime. Finish and packaging should take into account open-deck sea freight, if applicable. Lifting lugs should be provided for handling, shipping, and installation. The design should be such that the completed analyzer house is capable of withstanding the loads imposed by lifting, shipping, and other loads described below. Building design calculations should meet relevant DEP guidelines. The supplier should supply drawings showing the required layout of foundation beams and location of bolting to foundation, and should submit structural and/or civil design calculations as specified in the order. Calculations should be in SI units and in the English language. Furniture. An analyzer house should be equipped as standard with a workbench as a minimum. The design and construction of the electrical installation and the selection of the electrical equipment should be in accordance with the requirements of relevant guidelines. Electrical facilities inside the building should have a type of protection suitable for a Zone 1 hazardous area unless an alternative is specified by the principal. All electrical facilities inside the building which are not suitably protected for a Zone 1 hazardous area should be connected via industrial socket outlets that should be automatically isolated by an alarm and trip initiation system if a ventilation failure occurs. Distribution switchboards and terminal boxes. The electrical equipment in the analyzer house should be fed from the nearest electrical substation or switch room. The installation of local distribution switchboards in hazardous areas should be avoided. However, if such switchboards are required, they should be installed immediately outside the analyzer house in the least hazardous area, either on a free support with a weather cover or against that part of the wall that is protected from the weather. Segregated compartments should be provided for. Power distribution panel for electrical apparatus, emergency power distribution panel for fan, lights, gas detectors, if any, and HVC control panel, signal wiring termination, alarm signal wiring termination. At least 10% spare capacity should be provided in junction and terminal boxes. All wires should be identified at each termination with suitable wire markers that correspond to the appropriate wiring diagram. Electrical apparatus suitable for operation in the hazardous area should be connected via junction boxes unless hazardous area socket outlets are specified by the principal. Test equipment, electrical tools, and electrical equipment without adequate protection for the hazardous area should be connected to the electricity supply via general-purpose industrial-type socket outlets only. The supply to these outlets should be controlled by the instrumented protective system of the analyzer house. Earthing. An earth loop of 70 mm earthing conductors should be installed inside the analyzer house and should be connected to the plant earth ring. Signal cable shields should be earthed at a single point to the instrument earth in the control room. The integrity of intrinsically safe electrical apparatus should be retained. Metal parts of the building should form one electrical earthing continuity and should be bounded to the 70 mm earth loop. The earth bar of the switchboard, unless it is installed elsewhere, e.g. in the nearest substation FAR CCR, should be bonded to the 70 mm earth loop and the earth bar of the supply substation. Lighting. The luminaires used inside and outside the analyzer house should be fluorescent and of the same design as those used in the plant. Inside lighting should be suitable for a Zone 1 hazardous area. Permanent lighting should be controlled by switches installed at each entrance door. Emergency lighting should be provided by self-contained lighting fixtures or from the plant emergency lighting system. The lighting fixtures should be located inside the building above each door entrance. The illumination level inside the building should be at least 400 lux and should be provided by at least 2 lighting fixtures. A single light should be installed above each door entrance, and at least 2 lighting fixtures should be installed in each sample handling area. Exterior lighting should be controlled from the nearest substation lighting panel. If this is not possible, control should be by a photocell, but with a delay timer with an adjustable period of 30 minutes maximum. Ventilation and air conditioning of analyzer houses. General. The purpose of ventilation and air conditioning is to provide a safe operating environment for equipment and personnel, the required climatic conditions for optimal equipment performance, a sustainable climate for the comfort of personnel in line with local regulations and/or practice. Artificial ventilation of the interior of an analyzer house is required to achieve either dilution ventilation, the dilution of flammable gases and/or vapors that may accidentally escape from equipment inside the analyzer house to a non-hazardous level around any potential means of ignition. Overpressure ventilation, to prevent flammable and toxic gases from the outside atmosphere from entering the interior of the analyzer house. Both of the above, which is a normal requirement for analyzer houses located in an area where hydrocarbons are processed. Dilution ventilation and overpressure ventilation should comply with the relevant standards. The ventilation and air conditioning system should comply with general construction standards. Despite the absence of primary grade sources of release inside well-designed analyzer houses, the ventilation should not be demoted to a lower level, because it will never create the right conditions for a non-hazardous area inside the analyzer house. Artificial ventilation. Dilution ventilation is only practicable if the maximum possible rate of release is positively restricted. Therefore, the total amount of flammable fluids flowing to any analyzer accommodated inside the analyzer house should be limited by a properly adjusted excess flow valve. A limited flow of 100 liters per hour, at standard conditions, covers the need of most gas analyzer applications. The ventilation rate should be at least the greater of the following fresh air changes: 20 milliquarters per hour per analyzer, including those already installed and those projected for future spares. 12 volume changes per hour. As far as practicable, the flow through the analyzer house should be uniform and should not leave any stagnant pocket of air where flammable mixtures may develop. An economical method to obtain efficient dispersion may be by using an internal ventilation fan. The adequacy of the dilution ventilation should be checked against the maximum possible rate of release, taking into account the nature and hazard of the flammable material. For a liquid sample, the vapor load produced by the maximum possible rate of release should be used as the basis of this check. Overpressure ventilation. The pressure differential of the analyzer house with respect to ambient should be controlled to 50 pHa under normal design conditions and should be at least 25 pHa under minimum flow conditions, e.g., due to fouling conditions of the filter. Natural ventilation. Other premises which rely on natural ventilation, such as walk-in shelters and enclosed cabinets, should be subject to area classification according to relevant standards. Sample handling areas adjacent to the analyzer house fall into this category and should be designed so that they are not more severe than Zone 2. Absence of artificial ventilation. Enclosed analyzer houses requiring no artificial ventilation should comply with the requirements for non-hazardous areas. Air intake system and ducting requirements. The air intake should be through a stack provided with a rain hood and wire mesh bird screen. The air should be drawn from a non-hazardous area, and the air intake location should be at least 1 meter outside a hazardous area. The diameter of the stack and the intake duct should be sufficiently large to limit the air velocity inside the stack and ducting to a maximum of 8 meters per second. Inlet ducts should be airtight and should not pass through Zone 0 or Zone 1 areas. Inlet ducts should have connections for flow meters. A filter should be installed in the inlet air ventilation system so that it is easily accessible for cleaning or replacement. The size of the filter should be sufficient to require cleaning replacement not more than once per fortnight, or once per week in very dusty, e.g., desert, environments, under the maximum dust conditions expected. In cold climates, measures should be taken to prevent the filter from freezing up, e.g. by means of a slipstream from behind the ducting-mounted heater. Air should enter the analyzer house at ceiling level from ducting via openings with adjustable flow diverters to facilitate a proper direction and flow of air throughout the analyzer building. The ducting material should be corrosion resistant, e.g. hot-dip galvanized steel. The ventilation air should escape from the analyzer house through vertical ducts at 2 opposite corners of the analyzer house via louvers with adjustable openings. Ducts should either be installed on the outside of the short walls and connected to the interior of the analyzer house by openings in these walls, which are flush at floor and ceiling level, be triangular in shape, with two sides formed by the corner walls of the analyzer house and passing through the ceiling to the outside atmosphere. The inlet and exit port areas of the flow diverters and louvers should be adjustable to enable the trimming of flow direction and overpressure during the commissioning stage and later during normal operation. Openings in the air outlet ducting should be flush with the floor and ceiling to allow escape of gases and vapors, both heavier and lighter than air. The size of the ducting should be such that air velocities inside will not create noise levels that exceed acceptable limits. Outlet stack openings should be higher than any equipment, e.g. HVAC equipment installed on the roof of the analyzer house. Outlet stack openings to the atmosphere should be fitted with rain hoods and wire mesh bird screens. Adverse effects of outside wind direction and velocity on the ventilation and overpressure inside the analyzer house should be prevented by installing Nelson hoods or devices with similar features on the openings of outlet stacks ducts. Ventilation fan requirements. Ventilation should be by means of a centrifugal or axial fan with blades of non-sparking material and driven by a directly coupled motor. The ventilation equipment may be mounted either inside the analyzer house or outside, if suitably protected. Motors positioned inside ducting or elsewhere inside an analyzer house should have a type of protection suitable for operation in a Zone 1 hazardous area. The protection of motors installed outside the house should be in accordance with the classification of the outside area. The power supply to the fan motor should be independent of all analyzer house safety trip circuits. The fan speed should not exceed 2500 R-min. The fan support and casing construction should be sufficiently rigid to prevent resonance and vibration. The bearing support should be part of the fan casing. Heating. If duct heating is installed inside the ducting of an overpressure ventilation system, it should be de-energized in the event of ventilation failure if the heater is not suitably certified to continue operation in Zone 1. In all other cases, the duct heating should be de-energized upon ventilation failure if there is a risk of damage due to overheating by lack of sufficient cooling. Analyzer house protection. To ensure safety and compliance, analyzer houses must have adequate protection measures in place. These measures should account for potential hazards such as gas leaks, fire, and other emergency situations. The design and implementation of these protection systems should be thorough and align with relevant safety standards and regulations. Gas detection. Gas detection systems are essential for identifying and responding to leaks of flammable or toxic gases. These systems should be installed in strategic locations within the analyzer house to ensure early detection of gas leaks. Key considerations include sensor placement. Sensors should be positioned in areas where gas leaks are most likely to occur, such as near analyzer equipment, sample conditioning systems, and ventilation points. Type of sensors. Select sensors appropriate for the types of gases present in the analyzer house. Common types include catalytic bead sensors for flammable gases and electrochemical sensors for toxic gases. Alarm systems. Gas detection systems should be connected to audible and visual alarms to alert personnel in case of a gas leak. These alarms should be loud and visible enough to be noticed throughout the analyzer house and any adjacent areas. In case of a significant gas leak, the gas detection system should be capable of triggering automatic shutoff valves to isolate the affected area and prevent further gas flow. Enunciation, safeguarding, and IPF classification. Proper enunciation and safeguarding systems are critical for maintaining a safe environment within the analyzer house. These systems should ensure that any safety breaches are promptly detected and addressed. Important aspects include alarm enunciation. The alarm system should provide clear and distinct notifications for different types of emergencies, such as gas leaks, fire, or ventilation failure. These alarms should be both audible and visual. Safeguarding systems. Implement safeguarding systems to protect personnel and equipment. This includes automatic shutoff valves, emergency ventilation systems, and fire suppression systems. Instrumented protective functions of PF, Classification. IPF classification should be conducted to determine the level of protection required for each system. This classification should be based on the potential hazards and the severity of their impact. By ensuring these protection measures are in place and functioning correctly, analyzer houses can maintain a safe and compliant operational environment. Regular testing and maintenance of these systems are crucial to ensure their reliability and effectiveness in case of an emergency. Utilities and facilities. General. The analyzer house must be equipped with the necessary utilities and facilities to support the operation of the analyzers and ensure a safe working environment. These include air and water supplies, vent and drain systems, additional utilities, and telecommunication facilities. Air and water. Instrument air supply. Instrument air should be dry, clean, and free of oil or other contaminants. The supply pressure should be sufficient to meet the requirements of all air-operated devices and systems within the analyzer house. An independent instrument air header should be provided with isolation valves at key points for maintenance purposes. Cooling water supply. Cooling water should be provided if required for the operation of specific analyzers. The water supply should be reliable and capable of maintaining the required flow and temperature. Cooling water connections should be clearly labeled, and isolation valves should be installed for maintenance. Vent and drain systems. Ventilation system. The ventilation system should ensure a continuous supply of fresh air to maintain a non-hazardous environment. The system should include air intake and exhaust ducts, filters, and fans as specified in the ventilation design. Regular maintenance and inspection of the ventilation system should be conducted to ensure optimal performance. Drainage system. A suitable drainage system should be installed to handle any liquid spills or condensate from the analyzers and sample conditioning systems. Drains should be connected to a dedicated sump or collection vessel located outside the analyzer house. The drainage system should be designed to prevent any backflow of hazardous materials into the analyzer house. Electrical power supply. The analyzer house should be equipped with a reliable power supply, including emergency power for critical systems. Electrical connections should comply with safety standards and be clearly labeled. Backup power systems, such as uninterruptible power supplies, UPS, should be provided for essential equipment. Nitrogen supply. A nitrogen supply should be provided for purging and blanketing purposes. Nitrogen cylinders or a central supply system should be installed with appropriate safety measures. Connections and fittings should be compatible with the nitrogen supply and clearly labeled. Steam supply. If steam is required for specific analyzers or sample conditioning systems, a reliable supply should be provided. Steam lines should be insulated and equipped with appropriate safety valves and pressure relief devices. Steam traps should be installed to remove condensate and prevent blockages. Computers and telecommunication. Data acquisition systems. The analyzer house should be equipped with data acquisition systems to collect and process data from the analyzers. These systems should be compatible with the plant's central control system and allow for remote monitoring and control. Adequate data storage and backup facilities should be provided. Telecommunication facilities. Reliable telecommunication facilities should be installed for communication with the control room and other relevant areas. This includes telephone lines, intercom systems, and network connections. Emergency communication systems should be in place to ensure prompt response in case of an incident. By ensuring that these utilities and facilities are in place and properly maintained, the analyzer house can operate efficiently and safely, supporting the continuous and reliable performance of the analyzers. The inspection and testing of the analyzer house are crucial to ensure that all systems and equipment are functioning correctly and safely. This includes checking the building structure, utilities, ventilation, and other installed systems. Regular inspections and tests should be conducted in accordance with established procedures. Building, structural integrity. Inspect the analyzer house structure for any signs of damage, corrosion, or wear. Ensure that all components such as walls, roof, doors and windows are in good condition and securely fastened. Weatherproofing. Check for any leaks or gaps in the building that could allow water or dust ingress. Ensure that seals around doors and windows are intact and functioning. Fire protection. Verify that all fire protection systems, such as fire extinguishers, fire alarms, and emergency exits, are in place and operational. Conduct regular fire drills to ensure personnel are familiar with evacuation procedures. Utilities, vent and drain systems. Instrument air and cooling water. Test the instrument air and cooling water systems for adequate pressure and flow. Check for any leaks or blockages in the pipes and fittings. Ventilation system. Inspect and test the ventilation system to ensure it provides the required air changes and overpressure. Check the condition of air filters, fans, and ductwork. Ensure that the ventilation system is free from obstructions and operating efficiently. Drainage system. Verify that the drainage system is functioning correctly and that all drains are free from blockages. Check that the sump or collection vessel is properly maintained and emptied as needed. Heating, ventilation, and air conditioning systems, HVAC performance. Test the heating, ventilation, and air conditioning, HVAC, systems to ensure they maintain the required temperature and humidity levels inside the analyzer house. Check the operation of thermostats, heaters, air conditioners, and dehumidifiers. Filter maintenance. Inspect and replace air filters regularly to ensure proper air quality and system efficiency. Check for any signs of wear or damage to the filters. System calibration. Calibrate HVAC controls and sensors to ensure accurate temperature and humidity regulation. Verify that the system responds correctly to control inputs and maintains the desired environmental conditions. Inspections. Conduct regular visual inspections of all systems and components, noting any signs of damage, wear, or malfunction. Functional tests. Perform functional tests on all critical systems, including ventilation, air conditioning, gas detection, and fire protection. Document the results of these tests and take corrective action as needed. Maintenance records. Keep detailed records of all inspections, tests, and maintenance activities. Ensure that any issues identified during inspections are promptly addressed and resolved. By adhering to a rigorous inspection and testing schedule, the analyzer house can maintain a high level of safety and reliability. Regular checks and maintenance ensure that all systems function correctly and that any potential issues are identified and resolved before they become significant problems.